Okay, so calculating the reaction rate of one reactant from that of another. So what this question is getting you to do is write a relative reaction rate expression based on the stoichiometry of the balanced chemical equation. Of course, this question is really trying to test us by not giving us a balanced chemical equation. So I guess we should go forth and do that. So we've got a reaction between steam, which is water vapor, and gaseous methane, so that'd be CH4. So I suppose if we were being good, we should probably put our state symbols in, shouldn't we now? Produces syngas, synthesis gas, a mixture of carbon monoxide and dihydrogen. So let's balance that. Carbon monoxide would be CO gas, and then hydrogen would be H2 gas. So if we do a quick bit of accounting, we can see we've got 6 hydrogen atoms on the left side in the water and the methane, and 2 on the right side. And in fact, if I just put a coefficient of not 6, silly, 3 times H2 on the product side, we can see that that reaction is now balanced, because 3 times H2 will give me 6 hydrogen atoms on the right hand side. Okay, so to write a relative rate expression, this is going to get messy now. I've got to recognize that the change in concentration of the water over time, the rate of consumption of water, is going to be equal to the rate of change of concentration of methane over time, the rate of consumption of methane, which is going to be equal to the rate of production of carbon monoxide, the change in concentration of carbon monoxide over time. However, for each 1 mole of those other things that is being consumed or produced, we are producing 3 moles of H2 gas. So when we are writing our relative rate expression, the trick is that you put the rates equal to each other divided by their stoichiometric coefficient. So I'm just going to put a delta for the change in concentration of each of these and try and go ahead and write a relative rate expression as you do. So we're just setting these things equal to each other. So that's going to be minus. Oh, this isn't going to work very well at all. I'm just going to pause this a second so I can make it look pretty. You don't need to see my terrible drawing. Okay, that was a painful, excruciating draw using the computer mouse, so be glad that I spared you that. Okay, so we've written a relative rate expression. The only parts that are relative to what we're being asked is we're asked to relate the rate of consumption of methane to the rate at which dihydrogen is being produced. So we can ignore all of the rest of that. This question is a little bit tricky because we haven't been given the rate of consumption of methane, but we can work it out. Remember, concentration units, changing concentration over time, the rate is just expressing the amount of change of how much stuff we have over time. So I can see from here I have enough information to give me my rate of change of amount in moles of my methane, and again relate it to time because I've got liters per second. Okay, so in 1 second I can use the liters, the temperature, and the pressure to use the ideal gas law to work out my number of moles of methane being used up per second, and that is going to give me a measure of the rate. So PV equals nRT. Solving for n N is going to be PV over RT. So R is just the gas constant. T is going to be the temperature in Kelvin. And we've been given pressure and volume that is flowing in 1 second. So pressure is the 0.53 atmospheres. I'll tidy this up in a second. And the volume is 785 liters per second. R will be the gas constant in units of litre atmospheres per mole per Kelvin. That's 0.08206 litre atmospheres per mole per Kelvin. And then my temperature in Kelvin, well, I've been giving it in Celsius, so 172 plus 273.15 will give me my temperature in Kelvin. So let's just check the old units here. I should get moles at the end, so Kelvin we will be cancelling, liters we will be cancelling, atmospheres will be cancelling, and 1 over moles is going to give me my number of moles. Tappy 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 in my calculator, I get 11.39 moles of methane. Okay, so that is moles of methane per second. Okay, so I can then take my relative rate expression. I only need these two bits. Okay, so my rate, my delta change of CH4 in terms of moles. So I guess I could rewrite that. Delta, the number of moles of CH4 per unit time, which is just per second, moles of CH4 per second, is going to be 11.39 moles of CH4 per second. Okay, so now I can just substitute that into my relative rate expression, and I'm going to want to rearrange and solve for the change in number of moles of dihydrogen per second. So that means, see that 1/3 there, I am going to have to multiply my rate of change of moles of methane per second by 3 when I rearrange that. So my I should put my delta in. I'll come back and do it. My rate of change of moles of H2 per unit time per second is going to be 3 times whatever it was for my rate of change of moles of CH4 per second. So let's go ahead and tidy that up a little bit with lines. So my delta, my number of moles of H2 per second, 3 times my delta, my number of moles of CH4 per second. So that is going to be 11.39 moles per second multiplied by 3, which should shake out to be, what did I get? 34.17 moles per second of H2. Okay, so the last thing we need to do is convert moles per second to kilograms per second. So I'm going to use the molar mass of hydrogen, dihydrogen, to do that. So that's going to be 1 mole of H2 is 2 times 1.0079 grams. So that will be, molar mass is 2.0158 grams. So I can use that as my conversion factor. So I can take that 34.17, probably, moles per second, and I'm going to be converting that to grams per second. And then I've been asked for kilograms per second, and grams to kilograms, there's 1,000 grams in a kilogram, right? So let's get rid of the moles first. 1 mole of H2 contains 2.0158 grams. That's how much that is. So right now I've converted my units to grams per second, and then 10 to the power of 3 grams per kilo. I didn't write grams, silly me, per kilo. Okay, so if we just check our dimensional analysis, we should have moles cancelling out. We should have grams cancelling out. We end up with units of kilograms per second for the rate of production of H2, and I got that as 0.069 kilograms per second. Okay. All right. Hopefully that is helpful.